Hi everybody, today we're going to talk about the electrical force and Coulomb's law. Coulomb's law is the law and the equation that allows us to calculate electrical force. So our objectives for this lesson are to understand that charged objects exert forces, both attractive and repulsive forces, to utilize Coulomb's law to solve problems about electrical force, and to compare and contrast Coulomb's law with Newton's universal law of gravitation. We do that because there's a lot of similarities between the two, and if we can use Newton's law to understand a little bit about Coulomb's law, it might help us out. Okay, you might remember when you did your electrophorus in class. After you rubbed a piece of wool on the styrofoam plate, and you transferred some electrons there so that there was a net negative charge there, when you brought the aluminum pie plate close to the styrofoam plate, you might have actually felt a pull. And that's because there was an electrical force of attraction there. The styrofoam plate and the net charge on the styrofoam plate was trying to pull the aluminum pie plate down towards it. That's an electrical force. The rule with electrical forces is they exist between like and unlike charges. But like charges, meaning when we have two objects that are negatively charged or two objects that are positively charged, they repel each other. They push each other away. On the other hand, when we have objects with opposite charges, meaning one's positive and negative, they attract each other or they pull each other towards each other. So that attraction or repulsion between those charged objects is a force, and that is what is the electrical force. It's caused by the fact that those objects have charge. Electrical force is a very strong force. As a matter of fact, it's the source of most of the everyday forces that we observe in the world. A couple of rules about the electrical force. The force increases as the charge on the objects increase. So if you had rubbed your styrofoam plate longer with your little piece of wool and transferred even more electrons onto the surface of that styrofoam plate, it would have been charged even more, and you might have even felt a larger pull on your aluminum pie plate when you got closer to the styrofoam plate. The electrical force between the two charged objects depends on the distance between the charges. So you might not have noticed that force between the styrofoam plate and the aluminum pie plate until you got kind of close. When they were further apart, that force was much weaker. So the closer the objects are, the greater the force. The further apart they are, the lesser the force. And here's Coulomb's law. Coulomb's law is used to determine the magnitude or the size of the electrical force. It doesn't tell us anything about the direction, but that's okay because we can use our like charges repel and opposite charges attract to tell us the direction. So here's Coulomb's law. It tells us that the magnitude of the electrical force is equal to a constant that's called Coulomb's constant, represented with a little letter k, a lowercase k, and it's equal to 9 times 10 to the 9th newtons times meters squared divided by Coulomb squared. Some people call it the electrostatic constant, so you might hear it referred to as that. And then we multiply the charge on each of the objects in coulombs, Q1 and Q2, divided by the distance between the two charged objects squared. Looks very familiar to our Newton's universal law of gravitation equation. And just like that, let's look at that relationship just like we did with Newton's universal law of gravitation to see how the force changes based on what we change in our setup, be it our charge or our distance. So you might remember when you did your simulation for gravitational force with determining G, you graphed the gravitational force versus the mass. When you changed one of the masses, you looked and observed what happened to the size of the gravitational force. Well, we're going to do the same thing here. What happens if we graph the size of the electrical force when we change one of the charges? And just like with mass, because it's up in the top of the equation of Coulomb's law, that's a linear equation. So the greater the charge on an object, the greater the size of the electrical force. And then you might remember too that you did the relationship between the gravitational force and the distance between the objects. And if we did the same thing here, we compared how the electrical force changes as the distance between the objects changes, you would find that it looks very similar. It's that inverse square law. So as the distances between the objects get further apart, the force decreases, but it decreases proportional to the square of the distance between the objects. So what about the direction? If Coulomb's law only tells us about the magnitude or how big that force is, how do we know what the direction is? Well, first of all, we look at the charge. We see if the charge combination is like charges or opposite charges. If they're like charges, they push away from each other. If they're opposite charges, they attract or pull towards each other. But regardless of which way they do it, that force always acts on the line between the objects. Just like the gravitational force attracted two masses to their centers, same thing along here. That force would be along the line directly in between the charged objects. Let's do a little comparison of electrical force and gravitational force, just really quick to see how we can use one to maybe help us with the other. First of all, both the gravitational force and the electrical force are field forces, meaning that they act at a distance. They do not require contact to exert a force on an object. You can see that the equations are very similar. Right? We have a force that's equal to some constant. The electrical force is based on the charges of the objects. The gravitational force is based on the mass of the objects. And they both are those inverse square laws, meaning that as the objects get further apart, either the electrical force or the gravitational force, whichever you're looking at, decrease proportional to the square of the distance between them. Some differences, though, is that the electrical forces can be attractive, pulling towards each other, or repulsive, pushing away from each other. The gravitational forces are only attractive. They only pull towards each other. Also, the electrical force is very strong, while the gravitational force is relatively weak. And that's sort of obvious by the difference between their constants, those fudge factors that give us an idea about how strong the force is going to be. K is to the 10 to the 9th, whereas G is to the 10 to the minus 11th. G is a very small number. K is a very big number. Electrical force is a very big force. Gravitational force, a very small force. So there are some differences and some similarities between the two. Alright, so let's look at a few examples just to make sure that we're okay with using Coulomb's law to calculate the size of that electrical force. So now we have two charges. Each of them have a positive 1 Coulomb charge. They're separated by a distance of 1 meter. How large is the magnitude of the force between them? And we want to know whether or not it's attractive or repulsive. Because remember, Coulomb's law doesn't tell us about direction, it just tells us about magnitude. So let's write down our Coulomb's law. Fe equals kq1, the charge of the first object, kq2, divided by d squared. Okay, k is 9 times 10 to the 9th newtons times meter squared, divided by Coulomb squared, times our two charges, 1 Coulomb times 1 Coulomb. And since we're looking at magnitude only, you can leave the signs out of the charge, be them positive or negative, because we're just going to get the magnitude over 1 meter, whole thing squared. So you can see here that 1 Coulomb cancels out 1 Coulomb here, the other Coulomb cancels out that Coulomb here. The meters squared that you would get out of here is going to cancel out the meter squared up here. You're going to end up with our force in newtons. And this would tell us that we would have 9 times 10 to the 9th newtons of force. Now we would go back and say that's the size of the force, but we want to know whether or not this is an attractive force or repulsive force? Well, we want to look at it. Q1 is positive, Q2 is positive. So as a result, we have like charges, so our force is one of repulsion. They will push each other away with that force. Okay, let's look and see what happens when we halve the distance between the two. So we still have the same size charges. They're both 1 coulomb. So we're still going to have a repulsive force, but we now have them much closer together. So again, we'll just write down our Coulomb's law. Substitute our values. Times 1 coulomb times 1 coulomb. But in this case now, we have our distance as half a meter squared. So what we find, again, everything, our coulombs and coulombs cancel out. Our meter squared will cancel out with our meter squared, but remember we still square a number. We end up getting a force equal now to 3.6 times 10 to the 10th newtons. It's still repulsive. So we see it's greater than our previous force because they're closer together. But maybe we could have avoided doing all this work if we just realized that the only thing that changed was the distance between the two. So let's look at that kind of comparison way. If we knew that our original force between the two, excuse me, wrote the wrong number there, was 9 times 10 to the 9th newtons, and we wanted to know what the new force was, at half the distance, right? Because we went from 1 meter to a half a meter, we would just simply go, well, that new FE is equal to K. Our Q1 and Q2 did not change, right? The charge stayed the same, but our distance is now half of what it was before. So let's clean this up. We have K, Q1, Q2 still on the top, but 1/2 squared is 1/4, and our D squared is still D squared. And we see if we pull that 1/4 out and clean it up, that actually goes up into the top. We would get 4K Q1 Q2 over D squared. And you might remember that this is our original FE when we were at 1 meter away. So as a result, our new FE, we also could have just simply figured out this way and said it's 4 times 9 times 10 to the 9th newtons, which would have given us our 3.6 times 10 to the 10th newtons, which is exactly what we got when we did it directly. So a lot of times you can use that same type of relationship information that we did with Newton's universal law of gravitation to figure out how things are going to change when either the charge factor or a distance factor comes in. Okay, let's look at one example more, because when we start to talk about charge, you might remember I said in class that a coulomb is a really large unit of charge. So that 1 coulomb that I used in the previous example is not realistic and something that we would see. So we want to start talking about some numbers that we're kind of used to and that are more realistic and we might see in our problems. So now we have a small metal sphere. It has a net charge of +5. This guy here is a micro coulombs. It's one of our metric system prefixes. That indicates it's a smaller unit of measurement. And it's placed 2 centimeters from another metal sphere that has a negative charge now of 7 microcoulombs. Again, we want to determine the size of the force and whether it's attractive or repulsive. Now, the microcoulomb, you have to remember when you put the charge into the Coulomb's law, it has to be in coulombs in order to cancel out that coulomb in K, the constant. So as a result, I'm going to tell you, a micro is just 1 times 10 to the minus 6. So for ease of use, just do this. Cross out the micro and replace it with 5 times 10 to the minus 6. You don't even really have to do any conversion. If you know what the prefix means, you can just replace the prefix with its scientific notation replacement. Okay, so here we're going to do that. That makes things a little easier for us. We can plug them in right away in coulombs into our Coulomb's law. So this is going to be our 9 times 10 to the 9th newtons meters squared, coulombs squared. And those coulombs there are the reason that these have to be in coulombs. 5 times 10 to the negative 6 coulombs. And don't worry, even if it's 150 microcoulombs, your calculator doesn't care if the scientific notation is proper when you put it in there. And last but not least, just like these coulombs have to cancel out with those coulombs squared, this distance has to be in meters in order to cancel out with the meters squared. So remember that there are 100 centimeters in each meter, so this becomes 0.82 meters squared. Okay, we do all our calculations. Again, unfortunately, some of the scientific notation comes in with your calculator, so make sure that you're using that E key. Turns out to be a force of 787.5 newtons. And again, we have to say whether or not it's an attractive or repulsive force. In this case, we have a positive charge and a negative charge. So as a result, you can say it's a force of attraction. And you can see that I didn't even bother putting the negative and the positive into my Coulomb's law, because all it's going to tell me is how big it is. Now, if you happen to put the negative or the positive in for both, that's fine. Usually it also will tell you something about whether it's attractive or repulsive. If you end up with a positive size for your force, that means that your charges were like. They were either both positive or both negative. You would know it's a force of repulsion. If you end up with a negative number for your force, that would have meant one of your charges was positive and one of your charges was negative. So you ended up with a force of attraction. Just depends on what you want to do with it. Okay, and our last one is to realize that it's charge that has to go into Coulomb's law and not the things that cause the charge. So here we have 3 protons separated from a single electron by a distance. And again, we want to use Coulomb's law to find out the magnitude of the electrical force between them. So if you noticed here, you weren't given a charge in coulombs, but instead you were given the number of protons or electrons that's causing the charge. So for here, your Q1 is going to be caused by your 3 protons. So before you can even put that into Coulomb's law, you have to figure out the charge on those 3 protons. So we still use our fundamental charge of 1.6 times 10 to the negative 19th. It's positive because it's a proton. Per proton would tell us that this has a positive charge of 4.8 times 10 to the negative 19th coulombs. Alright, and our charge 2 would be because of the 1 electron. Right? And again, we know its charge is 1.6 times 10 to the negative 19th coulombs, but a negative charge for 1 electron. And our charge would be negative 1.6 times 10 to the negative 19th coulombs. Now once we have that charge, we can put that into Coulomb's law. We can't do that beforehand. It can't be the protons or the electrons. It actually has to be the amount of charge. So our KQ1, Q2 over D squared. So we go and substitute our values. To the ninth. Newtons, meters squared, coulombs squared. Running out of room here. Times my 4.8 times 10 to the negative 19th coulombs times my 1.6 times 10 to the negative 19th coulombs, all divided by my distance squared, and you can see these distances get pretty small. And I'm going to bring it up here just to make sure you're okay. And we end up with our force between these two is 6.9 times 10 to the minus 16th newtons. And again, the force would be attractive because they're oppositely charged. Hopefully that gives you enough information that we can start working on our problems in class when we come back. If not, come to class with questions. Thanks.